So let's take a look at these first questions. So maybe a little bit of recap. What did we do? We had the lecture on Bitcoin script, and first of all talked a little bit about transaction-based ledger versus the account-based ledger. And I see that account-based ledger is quite obvious. So a lot of people get that, how that works, how that should look like, and so on. But with a transaction-based ledger, it is not that intuitive. And these exercises are aiming to give you an understanding and to give you a little bit of an idea about what you can do with it and how Bitcoin handles these things. Because this is also, if you look at the exam, at the exams from last year, so they are available on GitHub. We linked this also in Moodle for if you didn't know that, and you can take a look at them. And this is where we also have some exercises on or questions in the exam, because I think that's very important to understand what's going on there. If you want to create your own blockchain-based systems, or you want to discuss about that, then you should be aware of the different models that exist here. So this is first exercises we do here are on transaction-based ledger, and to give you an idea what can happen, what can go wrong, and so on and so forth. So, okay, we take a look at the first question here is consider the following transactions on transaction-based ledger. Check if the transactions are valid. If valid, calculate the balances of each person. So we start with the first transaction. So that's a zero transaction, an empty transaction input, so some kind of mining reward. Transaction output, 25 Bitcoins to Bob. Okay, we can start about thinking Bob has 25 Bitcoins. Then we continue with a transaction input here. So 0, 0, the transaction 0 and the output 0 is used. So we look into the transaction 0, which is up here, and take the first transaction output, because we always we start with 0. So that's obviously very easy. It's the 25 Bitcoin that Bob received. We also check, is the signature valid? So signed by Bob. Bob received the money. Bob signed the money. So that's obviously also valid. Then we have a transaction output in terms of 12 Bitcoin to Bob, 5 to Carol, 8 to Alice. So obviously Bob needs to spend all the money here. So all these 25 is gone, but he sends himself 12 Bitcoin. So Bob has 12 Bitcoin left. Then Carol has 5 Bitcoin. And Alice has 8. And then we look in the next one. So we take that's the third transaction with transaction index number 2 is uses from the transaction 1 the third output. So 1, 2, 3. So Alice signed also this transaction. So Alice has not anymore these 8 Bitcoins, but she sends 4 to Carol and 4 to Alice. So Carol now has 9. Actually, she has 4 plus 5 because she needs to access these coins individually, so she cannot spend them at once. She has to address these transaction outputs individually, and Alice remains with 4. And then we see that the last transaction takes transaction 1 and index 2. So it's not Bob, but Carol. It's also signed by Carol, so that's valid. And so these are the 5 from Carol are spent. So we now need to spend these 5, and she gets 2 back. So it's 4 plus 2 for Carol, and Alice receives 3. So it's 4 plus 3. So the end balance should be like Alice has 7 Bob has 12 and Carol has 6. So if we look into the solutions, then that's correct. So Alice has 7, Bob has 12, Carol 6 transactions were correct. Yeah, I have to think about how I do it, how I want to share my iPad screen while having these transactions up there. How do we do that? Let me check if I can. Let's just make it like that. So this is what I did in terms of, okay, I created in terms of for each member in here, I basically created some kind of a line, and then I see if the balance changes or not. And yeah, so that's what I do. Basically, that's the that's somehow a little bit more efficient than anything else. Do it like that. Give me a minute, I can fix that. So then we doing this, and then I have to write a little bit bigger. Okay, then we go on. So going back to this one, 2b. That's also a not too difficult example here. What is wrong here? So first transaction is obviously correct. So we have again, Bob has 12.5. Then we spend the transaction from Bob. So Bob receives 8. Alice receives 2. And Carol receives 2.5. Carol 2.5. So what is the issue with that? That's fine, I think. That's, we can move on to that. So that's spent now. Then in the next transaction, so people write that I should write it bigger. Sorry, just now do it like that. It's ugly on the stream, but then you at least see something. Only for this exercises, and then we move it back. Okay. So we now finished, so that was transaction 0, and it was transaction 1. Then we have transaction 2, where Alice receives 12.5, so 12.5 here. Nothing else happens. And in the third transaction, we spent a second transaction or third transaction 0. So this one here. This one here. And then we now have 10 to Alice back. So 10 to Alice. And 2 to Bob. And 2.5 to Alice again. So what's the issue here? That's obviously 14.5, and that's a little bit larger than 12.5. And as we know, transaction inputs cannot be smaller than the transaction outputs. So this is the transaction input, and now it's the transaction output, so to say, and that's that's also transaction output. But so we consume these with a we consume this with a transaction input, and because that's where we provide the signatures, and this is where we create the new transaction outputs here. So this is obviously referenced to this. This is referenced here, and that's obviously again a transaction output. Okay. There is a question about that. I think we can take a look at that. So you, I can just remove the iPad right now. Why has the sum of outputs to be lower or equal than its input? The input represents how much was received in one of the previous transactions, not the current balance of a user. Very good question. So why need the sum of the inputs need to be larger or equal to transaction outputs, or the other way around? Why need the transaction outputs be lower than the transaction inputs? Because you are not allowed to spend more money than you actually have. So the transactions input represent the money you want to spend. So you reference to some transaction outputs that you own, or are in your name, or are in your public key, or in the hash of your public key, and the transaction output you create in your transaction is where you want to send the money to. So if I want to send the money to my colleague, then I have to specify the public key of her so that she can spend it in the future. So therefore, I only can spend the money that I have, and the difference between my inputs and my outputs. So if I have more money if I spend more money, if I have more money in my inputs than in my outputs, then this is considered as a transaction fee and goes to the miner. So that's the key point here. Okay, moving on. A little complicated. Okay, this is quite a large one. And I won't go into details about that, exactly what's going on here, but I just want to show you exactly what's going on in terms of transaction fees, because all these transactions are valid, so you can go over them as you would like. And so we have, as a result, comes down to Alice having 6 Bitcoin, Bob is having 9 Bitcoin, and Carol is having 7 Bitcoin. But the difference, the main difference is here, the problem, and is in transaction 1, for example. You see here, transaction 1 has a 0 as an input and spends 24 to Bob. And if you look into the 0 here, then Alice actually received 25 Bitcoin. So there is 1 Bitcoin lost, and this is considered as a transaction fee. So these are valid transactions, however, not optimal, or they definitely lose some money because of the transaction fee. And also in transaction 2, if you take a look here, it's 7 plus 12 plus 3, so 22. And they spend Bob's money here, 24. So again, here are 2 Bitcoins lost. Okay, moving on to the last one of these. So that you see the last ones here, and there is a little bit of a little bit mean from me to put this question there, because the amounts itself would add up correctly. However, if you take a look at the transaction 2, this output 1-1, and this output 1-1 here. Why don't you see that? Where's very good. So if you look at this transaction 1-1, then it's 1-1 and it's 6 Bitcoin to Alice, and only Alice can spend this, but it's signed by Bob. So Bob cannot sign outputs where Alice received money, so therefore this transaction is invalid. Okay, moving on. Again, a little bit larger. Below is the representation of 4 transactions in the Bitcoin network, where Alice receives Bitcoins from 2 different miners. Transaction fees are ignored. We have these 4 transactions. Again, transaction-based ledger. First transaction, the miner receives 12.5 Bitcoin, and in the second transaction, this miner spends it in terms of 3 to Bob, 1 to Carol, 5 to Alice, and 3.5 to himself back again. Then the third transaction here is, again, the miner 2 receives 12.5 Bitcoins, and this is spent to Alice, to Bob, and to miner 2. And Alice now wants to make 2 payments. She wants to transfer Carol 6 Bitcoin and Bob 0.5 Bitcoin. Draw the necessary transactions for Alice using the notation of the diagram above. So what is the key issue here? Let me take, if I can do some kind of... So we have Alice wants to spend money. So and 6 Bitcoin and 0.5 Bitcoin. And we have 2 transactions we can spend, actually, this one and this one. And as you see, she now has 2 transaction outputs. However, none of these transaction outputs satisfy the condition. So we cannot use only one to send both 6 Bitcoin to Carol and 0.5 to Bob. So what we have to do here is right now, she needs to combine her transaction outputs. And that's one of the properties, or one of the interesting properties of transaction based ledgers, that you can combine inputs and outputs. So in terms of, she received 2 transaction outputs, or she has 2 transaction outputs, and now she wants to create 2 transaction outputs for Carol and Bob, and also she wants to receive her money back. So the interesting thing here is we can create one transaction where we spend both transaction outputs, and we send both the money to Carol and Bob in one transaction, and also the money to herself. So how would this look like? So let me check if this. Let me do it like that. Not too fancy, but let's do it like this. And now we see we have again a box here. So we can have some transaction 5, and we have inputs here and we have outputs here. And what we need to do is basically we put all the inputs we want to do in there, and we want to put all outputs in there we want to create. So we use from transaction number 1 we use the output 2 because it's the third one. And then we wanna, from transaction number 3, we wanna use the first one. And so we now have two outputs we wanna spend. So these are in combination 8. So very well, now we can spend the money and create 2 transaction outputs for Carol and Bob. So what we can do is right now is we can say we want to send 6 to Carol and 0.5 to Bob. And now we have a little bit an issue because we have here right now 6.5 and we don't want to lose the remaining one. So we also send the remaining one back to Alice. And that's the trick. That's the magic. That's how it actually works in Bitcoin. So you can look at transactions. We can take a small look at. Let me take so that you see it for yourself. So we go to this, and then we have like an explorer, and then we can go into this tool, and then you see we have here are the first and the second inputs that they are using, and we have 3 outputs here. So that's what's going on here. As you see, and this can be combined arbitrarily. So these are just random transactions I pulled off from the web. So I have no idea what they are, what they mean, how much money it is. Not too little with 510 Bitcoins. But as you see, this can be arbitrarily combined and executed in one transaction. Okay, let's continue before we lose too much time. So if you take a look at the solution, exactly what I wrote down here with a little bit of a explanation. Okay, so moving on. We can now take a look at the blockchain explorers. So Bitcoin clients and exchanges provide block explorers that let users search transactions, blocks. Oh, maybe you should take a look at the tweet back. I'm sorry. Okay. 2 questions. Somehow my result for 1C is different. I proved it several times. Alice 6, Bob 9, Carol 4. So you said was C. Alice 6, Bob 9, Carol 4, and you have 7. You are missing that. So I will so where is Carol receiving? Carol is receiving 4 here. Carol receives 7 here. And Carol receives 3 here. Is this one spent to 1? No, it's not spent, but this one is spent. So the reason why you only get 4 is because you are missing this one. I would assume that you missed this one because this is never spent. This plus this equals 7. So that's the reason, maybe. Yeah, and also the new transaction be number 4, right? Not 5. Yeah, so 4. Sorry, I did this wrong in my iPad. Okay, continue. I showed the solutions here, but it's not too important because we just want to see how it looks like. So we want to take a look at the hash rate. We did this currently before. We just do this in Chrome again. So we go to blockchair.com. Now you should see something. And then we take a look at the Bitcoin blockchain and see what the current hash rate is. And 85.89 exahashes. So when I wrote here 98, that was some time ago, so it currently dropped a little bit. Okay, then the next one is what was the all-time peak value of unconfirmed transactions and when has it occurred? You might also take a look here. So when you go to this blockchain.com Explorer, you can do that again. Then you can take a look at the charts. And there are a lot of charts, millions and millions of charts, and not millions, but a lot more. And then you can take a look at, you have to search if there is something that fits what you need for. And so we have the memory pool in here. So that's actually what we need for. So the memory pool contains all unconfirmed transactions and when has it occurred. So we take a look in there and we see that we need to go like all time. And then you see, okay, there are too high needles here. And it's like May 1817. It's a little bit high. And also this one is, if we look here and if you fiddle around with the data, then you will find the solutions in terms of where's my box it here right now, then you will see it's at 185,000 at in December 2017. So that's what we did not see quite well there, unfortunately. But that's really just a number, not really too important, the exact number, but it's just an idea to discuss about what does this mean. So unconfirmed transactions obviously mean that some node has stored transactions which has not been included in the blockchain yet. So this has two relevant results. So first of all, it takes a longer time for the transaction to be included, obviously. So if the memory pool is full, it doesn't ever get full, but if there are so many transactions in there, then it takes some time until they are included in the blockchain. And the second thing is that the transaction fee rises. So the transaction fees for transactions is basically a market. So the more transactions want in, the higher the amount gets that software recommends for your transactions. So I tried it then actually. And my iPhone Bitcoin wallet, blockchain wallet told me, yeah, like you need to pay $40 for the transaction if you want to send that. So because they want to ensure that the transaction you send gets in the blockchain into a timely manner. You don't want to wait 1 or 2 days for that to happen. So they recommend to you fees which result in a high price and a fast time. And also the C question here is very interesting. I explain why there is no objectively correct number to the previous question. So what we asked before, what is the all-time peak value of unconfirmed transactions and when has it occurred? So unconfirmed transaction is a very subjective perspective because you are the node and only the transactions that are getting relayed to you can actually wind up in your memory pool or in this list of unconfirmed transactions. So if you have a very well-connected node, then you get lots and lots of transactions. And if you're a poorly connected node, then you might have trouble getting many transactions. And this results in that other nodes who are alive at the same time, alive in the same network, have a completely different view of the unconfirmed transactions. And I want to show you one example here. The Jochen Hönicke has a very well created website, and I really like that. I'll show it to you. And this is is the Bitcoin memory pool in terms of unconfirmed transaction count. And they give you the option to take a look at what's going on there. And it is very nice because it has some kind of sediments, and the sediments you see here, these colors, they are the prices, the transaction fees. So if you see these yellow parts here are transactions where they have which pay 40 or more Satoshi per byte. So Satoshi is the smallest unit, and you can calculate it in terms of per byte, how many Satoshis you want to pay. And so currently that's quite okay. But if you look at the highest count in terms of when it actually arrived in November 2017, then you really see people paid an awful amount of money for the transactions. And as you see here, at the highest value, it was 261,977. So it's the last line in this diagram here. And you see it's a hell of amount of transaction. It's totally different to the transaction count that blockchain.com provided to us. Okay, then let's move back to the sheet. And take one question from Tweetback. It is also because each node maintains its own local memory pool. Exactly. So that's what I wanted to say, or that's the message of my talk. Every node maintains their own memory pool, fills it, and so that's very subjective. Okay, moving on. This is a question. Find a transaction, fill in the following information. And that's really not difficult. You take this information, copy it into a block explorer if you're liking, Blockchain, blockchain, whatever, and see what's happening in there. So I won't go into too much details here. The solutions are up today at 18 o'clock p.m. and then you can take a look at it. The only interesting thing I want to talk about is the value of the transaction and what is interesting about the transaction. So let's take a look and go here, put it in here. It's in Bitcoin. And then you see it's 10,000 Bitcoins that were sent in here. And you actually need to Google this address to understand what's going on here. But this was this transaction in 2010 where some guy bought the first pizza or the first 2 pizzas for 10,000 Bitcoins, roughly 10,000, roughly 30 euros or $30 back at the time. And yeah, that's the interesting part about this transaction. It's all history. It's all available in the blockchain at the tip of your fingers. So take a look. Okay, now we continue with the Bitcoin script. Bitcoin script is the programming language that we can use in Bitcoin. And there's one good question just arrived on Tweetback, so I'll skip back to this former question here about this transaction. Sorry, I'm a little bit through the wind today. I don't know what's going on. So the user claims or student claims, when I checked this transaction, I found 3 results: Bitcoin, Bitcoin Cash, and Bitcoin SV. It stands for Satoshi's Vision. Can you explain Bitcoin Cash and Bitcoin SV? So Bitcoin is a The problem with Bitcoin is that it's we have the longest chain rule. So as we briefly mentioned before in the lecture yesterday, the longest part will always survive. And as we will see next week, there are some, we need to think about how can we update Bitcoin. So Bitcoin itself needs to be updated. We need to patch some security issues. Maybe we want to do also enable future new cool stuff. So we need to think about how we want to build this further. And one rule was, which Satoshi Nakamoto claimed in 2011, that the block sizes should not be larger than 1 megabyte. And this led to this dramatic increase of transaction fees, because the blockchain can only process 3 to 6 transactions per second. And this resulted in 2 different proposals. So people said, okay, we need to increase the block size. And basically the community split into Bitcoin and Bitcoin Cash. Bitcoin Cash supports now until 256 megabytes of blocks, so really huge blocks. And Satoshi Vision is a blockchain which actually has other properties which I don't know, or don't know too much in detail. So, but these are different blockchains which run almost identical software, but have a common history. So because these chains split at some point of time into different directions, they created separate realities. Their history in terms of this 10,000 Bitcoin transaction where someone bought pizza is identical on all these 3 chains. But if you look into current situations, then these chains are totally different and the transactions are not alike. So that's what's going on there. Then also the question is, why are so many inputs being used in the Dvir transaction? So that's the reason I said again, so these are over 130 inputs there, it seems to be. And the reason for that is that the person who sent these 10,000 Bitcoin did not receive 10,000 Bitcoin in one transaction, but in many, 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 many transactions. And the guy needs to combine all these outputs into one single transaction. Otherwise, he cannot spend it as a single transaction. The fee itself, there's also the question about the fees here. So the fee is here 99 Bitcoin, 0.99 Bitcoin. So that's definitely in there. So all transaction outputs combined to 10,000 and 0.99 Bitcoin. That's true. Okay, let's continue with a Bitcoin script. So, Bitcoin script, again, this is the language where we can define how money can be spent. That's a very powerful property. That's a very powerful language, in my opinion. So it's obviously not that powerful in terms of Turing completeness. So we will take a look at Ethereum and Solidity, where they have a Turing complete language. And it's limited in what it can do, Bitcoin script. But because of that, people underestimate it often in terms of, okay, it's only there for sending money from A to B. But if you look at advanced concepts like payment channels or Lightning Network, which we unfortunately do not cover here because of time issues, but these are really, really interesting proposals going on there. And we have to take a look at that. If you wanna see what's really going on. So take a look at the Bitcoin script opcodes in the slides. Which fundamental comments are missing? What could be reason for that they are not added? So we can take a look at the slides here and see what's going on there. I think quite interesting. And oh, that's the wrong slide set. Sorry for that. Okay, so when we look at the basic, what can Bitcoin script do? These are some of the comments that's in there. And it actually says exactly what we need to know or what's missing. And it's, so we have some flow control in there, but we cannot loop anything. We also have no other, so there are a lot of so this loops are obviously missing, but all the other interesting methods are missing. So if you look at arithmetic is disabled, we cannot do any string operations, we cannot, so some cryptographic operations obviously available, but apart from that, all the interesting stuff, we cannot calculate anything, we cannot yeah, whatever we want to do is very limited in this usage. Let me check. Let me check what's also not in there. So loops or jumps, as I said, and the reasons for that that we do not have it in there is because of the halting problem. So the idea is that you want to have scripts that can be easily executed and checked. And if you were able to create a script that, for example, would never finish, then you could basically render the Bitcoin network unavailable. So that's the big issue here. And also every complexity, every increased complexity of the Bitcoin script leads to the fact that the attack surface is getting bigger, and we really want to reduce this, and we really want to prevent this. So making the system secure by reducing the complexity as much as possible. So that's the important point here. And in Ethereum, you will see it that we have loops and jumps, so they support it. And how they solve the halting problem, we will see in the next chapters. Let's continue. So Alice wants to protect her Bitcoins and therefore her unspent transaction outputs. She decides to protect it with a password. She hashes the password and writes a script. The script requires the person which intends to spend the output to provide the password as an input. So this intent to spend the output, this person, is obviously herself. So because she wants to secure it, she wants to spend it later on. This input is hashed and compared to the predefined hash, proving that Alice spends the transactions. What are possible flaws with this Bitcoin script? So let's take a look about this Bitcoin script here. So we have a password, and this password we hash it. And then we get some kind of hash here. That's our hash. And if you look at the Bitcoin slides, we have a interesting part here in terms of you look at this one. We have this script here, and what it actually does is it takes that's the public, the pay to public key hash, and this is also where information is hashed and where information is compared. So we can take the script and remove parts from it and get basically what we need. So what we need is basically, we need this op hash, switch back here, and this op hash 160, and we need this our hash basically, and we need this op equal verify. So what we could do basically is, if we now look this from a stack point, then we would have some kind of this one here. We have our, that would be our script sig. That's what we provide as a transaction input. That's our script pub key. The script that actually Alice has set up in terms of, okay, we need this op hash. We need our hash here that we compare to. Then we need our op equal verify. And this is basically our password. So what would happen in the first step, this password gets put on the stack. In the second step, this is hashed, so to say. Then we have, let's remove this one here. Then we put this one on the stack, the actual hash. And now we do some kind of op equal verify in terms of, are they similar or not? So that would work. What is the issue with that? I don't get it. So the main problem here, why this is a bad idea to do that, is that you actually prove that you can spend, that you can unlock this. You prove that you can spend this script pub key. But the problem is that you cannot put an intent on it. So what is an intent? Intent means that you want to make sure that the money you own because of the script pub key here, that it goes in the direction you want to. So you can spend money, but you would also want to make sure that it's actually getting to the place, to the receiver. And if you do an approach like that, there is no way for you to actually say, okay, I want to go in that direction. So you can obviously, the transaction itself that you created now, this new one, obviously contains this script signature, your password, and so on. And it contains also this new script pub key where you want to send the money to. But the miner, before receiving your before including your transaction in the block, could say, okay, remove this one, and let's create my own one here. Let's write a new one in here. And the transaction is still valid. And that's the key here. So we cannot use hashes as a property of proving something. So we can use that, but it's a bad idea. We need to rely on signatures for that to happen. So that's the very important part. If you want to send money, if you want to use Bitcoin script and do not rely on signatures, then you're going to have a bad time. Obviously, there are some, for example, you could use this as a puzzle in terms of, okay, you think of some kind of digital quest for people, and the end result, this is the password. Then obviously you can do something like that, but still that money can be stolen from the actual winner. So that's really the problem here. So let's take a look at the question. Where exactly is the signature of a transaction stored, i.e. the signature of the sender of the transaction? So this is actually in the transaction input. If you look at the slides here, then you see the script signature input here, script sig, and this is where the signature is in there. And the signature not only tells, okay, it's okay to spend the money, but it also includes information about the transaction outputs, the new created transaction outputs. what is actually hashed when checking the signature? A fingerprint of every transaction input used, right? So what is actually, what does the signature contain? So the signature contains a lot of things, and we did not cover this because it's too complicated, but you can think of it, it contains the transaction you want to create as whole. So obviously there is no redundancy in there, but the transaction you want to create is protected by the signature. You cannot change anything on this transaction without making it invalid. So if you want to change something, you need to have the private key. So the miner could replace the script pub key. Exactly. So that's the problem with this exercise 5 here. If you do it like Alice here, then the miner can replace the script pub key, and no one can prove that actually that the miner did that. So there is no way to do that. In short, can we tell there is no verification of identities and anyone who knows the password can spend it? Exactly. Anyone who knows the password can spend it, and also anyone who gets to know of the password before it's actually mined into a block can spend it. So that's the problem. Okay, so let's move on. We have a very good question here, and I like, because we explained both in the lecture. We covered both in the lecture. We have an opcode called log time verify and a time lock in the transaction itself. What is the difference? What are examples in which these are useful? So the opcode log time verify is something that it's placed into a transaction output. So it can be mined instantly. So a transaction which contains an transaction output with a log time verify, then it's no issue. It can be mined directly. The time lock in the transaction itself is a way to ensure that a transaction is not included before a certain point of time in the block. So time is obviously, or time is given as a height of the current block. So because every 10 minutes a new block gets created, that is quite well estimate for time. And so this transaction cannot be included before this time lock basically unlocks. And what is the usage here? And for example, the time lock itself is for micropayments. So we had this micropayment channel example, yeah, and this included had some. We want to basically ensure that money does not get spent before a certain point of time. So we had it. Where did we had it? We had it here. So Bob basically does not pay Alice back the money until a certain point of time. So to make sure that Bob actually has some time to claim his money, and but also as a guarantee for Alice to basically get back the money. And for example, for this log time verify code, that's something where you say, okay, I want to make sure that a money cannot be spent for a certain period of time. So for example, there are some companies, some startups out there who say, okay, we create this new blockchain and we want to collect some funds, and they can collect these funds. Should not collect these funds for a certain period of time. So they want to make sure that they have it, that they receive it, that they will get it. But the people want them to continue building and want to have an incentive for them to not just drive off with the money. So what they can do is basically they can create some log time verify in there and lock the money for a year, for 6 months, stuff like that. But the money is definitely there. And with a time lock in the transaction, the money could be gone, because that's the intent of this micropayment channels here. Okay. Let's continue here. Maybe take a question from Tweetback. Back to question 5. How would the miner benefit from replacing script pub key? That's again the question in terms of where Alice used the password as a transaction as for the script pub key. The miner would benefit from that because he could steal the money. So instead of Alice paying Bob, the miner could say, okay, Alice is now paying me. And obviously, as an economic rational miner, you would say, okay, free money is good money, and now it's mine. So that's the reason what the miner would do here. Okay. Last question for this exercise sheet. And I think that's a one where you get a little bit an idea again and better understand what's going on with script signature, transaction output, transaction input, script pub key, because this is that's a very well example. So following transaction output is provided. So opt up, op hash 160, some kind of weird hash, op equal verify, op checksig. So that's the basic pay to public key hash example that we use in the lecture. So question A, can you tell which entity has created this transaction output? So transaction output is basically the where we want to send the money. So this, anyone who can solve this script receives the money. So can we tell who created this transaction output? No, because we do not see the respective transaction input. We do not know the overall transaction. This is just a part of the transaction. And we will need to see the other half, so the transaction inputs, to see actually who spent the money or who created this transaction output. B, can you tell if this transaction output is spent or not? So as we just look at the transaction output, a part of the transaction, and we do not know the circumstances of the network. So we cannot tell if this transaction has been spent or not. We just can tell. We don't have a look at the blockchain. We don't see anything. So therefore, we cannot see that. C, can you tell which entity is allowed to spend this transaction output? So as I said, this script enables the one who or defines who is able to spend the associated money. And so we should be able to tell which entity is allowed to spend this transaction output. And as we look here, and if you look at the slides, then you will see that this is the magic information here. All the other, everything else is standard, but this is a hash, and this is the hash of the public key of the person who is allowed to spend the money. So you would be able to say, okay, the person who owns the private key to public key to the hash of this is able to spend the money. So that's an invalid answer. And this is again more precise in the D. What specific data is required to spend the transaction output? It's obviously the private key. So the private key to the public key to the hash of this is the data we need to spend this transaction output. Obviously, we need a little bit more in terms of which transaction is it, stuff like that. But the specific data here, which is unique, which is secret, is the private key.